Picture this. Imagine every nuclear bomb ever built on Earth. Detonate them all at once. Now multiply that unimaginable power by 1 billion. Then multiply it again and again. You are still not even close to the energy unleashed by a single gamma-ray burst. These events are the most powerful explosions the universe has known since the Big Bang itself. They are cosmic behemoths, capable of outshining entire galaxies for a few fleeting, terrifying seconds. The energy they release in that short time is more than our own sun will produce in its entire 10 billion-year lifetime. We are talking about forces that defy our everyday comprehension, phenomena that remind us just how small we are in the grand cosmic theater. These are not your average stellar flares or distant supernovas. A gamma-ray burst, or GRB, is a class all its own. It is a focused, directed beam of pure, high-energy radiation, a cosmic death ray traveling across billions of light-years. When one of these goes off, it is briefly the brightest object in the entire observable universe in the gamma-ray spectrum. Think of the universe as a dark room. Most events are like flickers of a match. A supernova is like a flashbulb, but a gamma-ray burst? That's a searchlight so intense it can be seen from the other side of the room, even if it only flashes for a moment. Its sheer luminosity is staggering, a testament to the extreme physics at play. The very existence of these bursts challenges our understanding of physics. How does nature conspire to create such a focused, cataclysmic release of energy? The answer lies in the most extreme objects and events the cosmos has to offer: the death of colossal stars and the birth of black holes. These are not gentle goodbyes, they are violent, universe-altering transformations. The energy is so immense that it is almost impossible to model accurately. We are peering into the heart of processes that push the laws of physics to their absolute breaking point. It's a realm where matter is torn apart and space-time itself is warped under the strain of unimaginable forces. For decades, these flashes of light were a complete mystery. We saw them, but we didn't know what they were or where they came from. They appeared randomly in the sky, flared with unbelievable intensity, and then vanished without a trace, leaving astronomers baffled. They were cosmic ghosts, transient specters that haunted our telescopes. It took dedicated satellites designed specifically to hunt for these fleeting signals to even begin to piece together the puzzle. Each new observation adds another layer to the story, a story of cosmic violence, creation, and the fundamental forces that govern everything. The universe, it seems, has a flair for the dramatic. So what exactly is a gamma-ray burst? At its core, it is a flash of gamma rays, the most energetic form of light. This isn't the visible light our eyes can see or the radio waves we use for communication. This is high-frequency, high-energy radiation. A single photon of a gamma ray carries more energy than millions of photons of visible light combined. These bursts are detected by specialized telescopes in orbit, high above Earth's protective atmosphere, which thankfully shields us from this kind of radiation. The mystery deepens when you consider their duration. Gamma-ray bursts come in two main flavors: short, long. Short bursts last less than 2 seconds, sometimes just a few milliseconds. They blink in and out so fast they are hard to pinpoint. Long bursts can last from a few seconds to several minutes, a veritable eternity in high-energy astrophysics. This difference in duration was a major clue. It hinted there wasn't just one type of cosmic event, instead two distinct, yet equally violent phenomena. The universe has multiple ways to create a cataclysm. Their rarity is another part of their mystique. Our satellites detect about 1 GRB per day, coming from all over the observable universe. The events are incredibly rare within any single galaxy. Odds in our Milky Way close enough to worry, perhaps once every few 100,000 years. But the key: they are not spherical explosions. They are beamed, like a laser. The energy isn't wasted spreading in all directions. It's concentrated into two narrow jets, Jet 1, Jet 2, racing away from the source at nearly the speed of light. This focused nature is why we can see them from so far away. If a GRB were isotropic, spreading energy evenly, it would be far too faint from billions of light years. But because the power is channeled into a narrow beam, it stays intensely bright along that line of sight. For every 1 GRB we detect, there are hundreds more we miss because their beams weren't pointed at us. We only see the ones aimed directly at Earth. The universe is filled with cosmic lighthouses, their beams sweeping across the void, and we only ever see the flash. Where do these monsters come from? The answer is as dramatic as the bursts themselves. Long-duration gamma-ray bursts lasting more than 2 seconds linked to the deaths of the most massive stars. Not stars like our sun. Stellar titans more than 30 times the sun's mass, more than 40 times the sun's mass. They burn fuel at a furious pace. When they die, they don't fade away. They explode in a hypernova, a supernova on steroids, an explosion that tears the star apart. As the core collapses, it forms a black hole, but it's not quiet. Outer layers rain down on the forming black hole. A chaotic superheated accretion disk forms. A swirling vortex of matter spinning near light speed generates powerful magnetic fields. Fields act like a cosmic particle accelerator. They trap superheated plasma and funnel it out along the poles. Two ultra-relativistic jets form, Jet 1, Jet 2. The jets blast out of the star. When they break free, they unleash a gamma-ray burst. Short-duration GRBs have a different origin, from cosmic collisions. Two neutron stars, Object A, Object B, ultra-dense remnants, locked in a gravitational death spiral. They emit gravitational waves, lose energy, spiral closer and closer together. The final moments are catastrophic. They merge in a kilonova. The collision forges heavy elements, gold, platinum. It also launches short-lived jets, creating a brief, intense, short GRB flash. A GRB signals the birth of a new black hole or a merger forming one, the universe's most violent birth announcements. One of the most mind-bending discoveries about gamma-ray burst vertical bar is just how far away they are. The most distant GRB ever detected, an event designated GRB 090423, exploded when the universe was only about 630 million years old. That's less than 5% of its current age. The light from that explosion traveled for over 13 billion years to reach our telescopes. This means we are seeing the death of one of the very first generations of stars. These first light stars were cosmic behemoths, made almost entirely of hydrogen and helium, and they lived fast and died young. GRBs are our only direct window into the end of their lives. An even stranger discovery came in December 2021. Astronomers detected a GRB that seemed to defy our models. This burst, named GRB 211211A, was a long-duration burst, lasting for nearly a minute. According to our theories, it should have come from a collapsing massive star, but its location and the afterglow it produced told a different story. The evidence pointed not to a hypernova but to a kilonova, the merger of two neutron stars. This was a shock. It suggested that neutron star mergers, which we thought only produced short bursts, could under certain circumstances generate long-lasting ones. The neat dividing line between our two models was suddenly blurred. The story of the Christmas burst of 1997 is another fascinating chapter. On December 14th, the BeppoSat satellite detected a GRB. For the first time, astronomers were able to quickly pivot ground-based telescopes to its location and observe its afterglow, the fading embers of the explosion in visible light, and other wavelengths. This was a monumental breakthrough. It allowed them to pinpoint the burst's origin to a specific faint galaxy billions of light-years away. This discovery single-handedly solved the decades-old debate about where GRBs came from. They weren't in our galaxy, they were truly cosmological, originating at the far-flung edges of the universe. Another curious tale is that of the naked gamma-ray bursts. For a while, astronomers were finding GRBs that had no visible afterglow. These were called dark bursts, and they were a deep puzzle. Were they a new type of object, or was something blocking the light? It turns out that many of these bursts were happening inside incredibly dense, dusty, star-forming regions in their host galaxies. The gamma rays, being so energetic, could punch through the dust and gas to reach us, but the lower energy visible light of the afterglow was completely absorbed. These discoveries remind us that our view of the universe is always filtered, and sometimes we only get part of the story. To truly grasp the power of a gamma-ray burst, comparisons are essential, even if they kinda strain the imagination. So let's go back to our sun for a moment. In just 1 second, the sun produces a tremendous amount of energy. But, get this, a typical long-duration gamma-ray burst in that same 1 second can release more energy than 100 quadrillion suns combined, one with 17 zeros after it. Think scale, a lit match, a nuclear bomb, the sun, a supernova, and a gamma-ray burst. For the few moments it's active, the burst is the undisputed king of the cosmos, outshining every other star in the observable universe put together. Honestly, it's a level of power that has no parallel. Let's compare it to a supernova. A powerful supernova releases about 10 circumflex 44 joules of energy. But a gamma-ray burst can release about 10 circumflex 47 joules into its narrow beams. That is 1,000 times more powerful. The supernova explodes in all directions, while the GRB focuses its energy into tight beams. It's like a bomb going off, versus a shaped charge designed to punch through armor. The GRB is a weapon of cosmic precision and overwhelming force designed by nature to be seen across the universe. Now think about the energy in terms of matter. Einstein's famous equation, E equals mc squared. Mass and energy are two sides of the same coin. The energy in a powerful GRB is equivalent to converting several Earth masses of matter into pure energy every second. Imagine taking our entire planet and, in the blink of an eye, turning it into a beam of radiation. That's the physics at the heart of a collapsar, or a neutron star merger. It's the universe's ultimate conversion engine, turning matter into raw, untamed energy with terrifying efficiency. Even when we look at the most powerful objects we know of, like quasars, a quasar is a supermassive black hole at the center of a galaxy. It feeds on gas, it feeds on stars, and it can shine with the light of 1 trillion suns. A quasar is a beacon of immense, sustained power, but that power is spread out over millions of years. A GRB unleashes a similar amount of energy in just seconds. It's the ultimate cosmic sprint versus the ultimate cosmic marathon. The GRB is all about shock and awe, a sudden blinding flash that rewrites the energy budget of its entire galactic neighborhood in an instant. So, what would happen if one of these cosmic death rays were actually pointed at Earth? Honestly, the scenario sounds like pure science fiction, but the physics behind it is very real. Now let's be clear here, the probability is exceedingly low. For this to even happen, the event would need to take place within our own galaxy, relatively close by, like within a few thousand light years, and its jet would need to be aimed precisely at our tiny blue dot. It's kind of like trying to hit a moving dime from 1,000 miles away with a laser pointer. But if that cosmic lottery ticket did come up, the consequences would be absolutely catastrophic for life on Earth. First off, we wouldn't even see it coming. Gamma rays travel at the speed of light, so there would be no warning at all. The very first sign would be a sudden flash of intense radiation washing over the sunlit side of the planet. This gamma radiation would slam straight into our upper atmosphere. X-ray radiation would slam straight into our upper atmosphere. It wouldn't reach the ground. Our air is actually a pretty good shield. But it would trigger a series of devastating chemical reactions. It would tear apart nitrogen molecules, it would tear apart oxygen molecules, creating massive amounts of nitrogen oxides. These molecules would then go on to destroy the ozone layer, which is our planet's critical shield against the sun's ultraviolet radiation. Within just a few weeks, the ozone layer could be depleted by as much as 70% globally. That would allow deadly levels of ultraviolet or UVB radiation from our own sun to reach the surface. This intense UV radiation would be devastating for life. It would cause severe sunburns in humans and animals within just minutes of exposure. But even more importantly, it would fry the phytoplankton in the oceans, those tiny microscopic organisms that form the base of the entire marine food web and produce a significant portion of our planet's oxygen. The collapse of the marine ecosystem would be swift and total, and the consequences on land would be just as dire. The increased UV radiation would damage crops and it would damage forests, leading to a global agricultural collapse and widespread famine. The nitrogen oxides created in the atmosphere would also fall back to Earth as acid rain, further poisoning the land and water. The combined effects, the collapse of the food chain, the destruction of agriculture, and the direct harm from UV radiation, would trigger a mass extinction event on a scale not seen since the dinosaurs were wiped out. Some scientists have even speculated that a past mass extinction, the Ordovician-Silurian event, about 450 million years ago, might have been caused by a nearby gamma-ray burst. It's honestly a sobering reminder that the cosmos can be a pretty dangerous place. The universe that creates gamma-ray bursts is filled with other strange and wonderful phenomena. Take the objects that cause them, neutron stars. These are collapsed cores of massive stars. A single teaspoon of neutron star material would weigh about 10 million tons on Earth. City-sized spheres, the mass of a star, spinning hundreds of times per second. When two of these cosmic spinning tops collide, they create a gamma-ray burst. They warp space-time and send out ripples called gravitational waves. We can now detect those ripples here on Earth. Then you have the black holes born from these events. A stellar mass black hole packed several times the mass of our sun into a sphere just a few miles across. Its gravity is so strong that nothing, not even light, can escape the event horizon. But black holes aren't just cosmic vacuum cleaners. Thanks to Stephen Hawking, they can slowly evaporate by emitting Hawking radiation. A tiny black hole would evaporate in a flash of gamma rays, like a miniature gamma ray burst. The universe's weirdness doesn't stop there. It extends to planets too, planets orbiting pulsars. Pulsars are rapidly spinning neutron stars. These pulsar planets are some of the most extreme worlds imaginable. They're bathed in intense radiation from their dead star, a far cry from Earth's gentle warmth. How they form or survive is a major astronomical puzzle. They exist in a graveyard of a solar system, showing planets can survive even around supernova remnants. And let's not forget the cosmic web. Galaxies aren't scattered randomly. They're arranged in filaments and voids, resembling a gigantic cosmic spiderweb. Filaments are long, thin strands of dark matter. Galaxies strung like pearls on a necklace. Gamma-ray bursts explode within these galaxies, sending beams hurtling through the voids and along the filaments. The light from these bursts travels across the cosmic web for billions of years, carrying the story of the universe's structure in earlier, more violent times. With every new discovery about gamma-ray bursts, a dozen new questions seem to pop up. We've learned so much, yet what we know is absolutely dwarfed by the vast ocean of what we don't. We still don't fully understand the precise mechanics of how the jets are launched. What is the exact role of the magnetic fields? How do they collimate the energy with such incredible efficiency? How can neutron star mergers sometimes produce long bursts? Every observation that challenges our models isn't a failure. It's actually an opportunity, a signpost pointing toward new physics that we haven't even dreamed of yet. That's the real beauty of science. It's a journey, not a destination. Our cosmic ignorance isn't a flaw, it's the engine of our curiosity. The universe is under no obligation to make sense to us, and the fact that it sometimes does is just the most wonderful thing. The fact that we, a collection of atoms forged in the hearts of stars long dead, can build instruments to look back across 13 billion years and witness the death of another star, is a profound achievement. It connects us directly to the cosmos in the most intimate way possible. We are, quite literally, stardust contemplating the stars. The universe is vast, dark, and filled with mysteries. There are gamma-ray bursts, black holes, dark matter, and dark energy. The latter two make up 95% of the universe, and honestly, we have almost no idea what they are. We're like explorers who have just landed on the shore of a new continent, with the entire interior shrouded in mist. We've mapped the coastline, but the real adventure lies in the unknown lands ahead. Every new telescope, every new observation, pushes that mist back just a little bit further, revealing a landscape more complex and beautiful than we ever could have imagined. The universe is talking to us, telling its stories through light, through gravity, through flashes of gamma rays from the edge of time. It's a cosmic conversation that's been going on for 13.8 billion years, and honestly, we've only just started to listen. What other cosmic mysteries are waiting out there for us to uncover? What are the questions about the cosmos that keep you up at night? Let us know in the comments below. We really want to hear what puzzles and fascinates you about our incredible universe. The exploration of these cosmic phenomena is a shared human journey. If this dive into the universe's most powerful explosions sparked your curiosity, then help us spread that sense of wonder. Please like this essay and share it with your friends, your family, anyone who loves to look up and marvel at the great unknown. Your support helps us continue bringing the cosmos down to Earth, one mystery at a time. It allows us to keep asking the big questions and searching for the even bigger answers that are scattered among the stars. And of course, if you want to join us on more journeys to the frontiers of science, from the heart of a black hole to the farthest reaches of the observable universe, be sure to subscribe. We have so much more to explore together. The universe is a big place, and honestly, we're just getting started. By subscribing, you won't miss a single step of our ongoing mission to understand our place in the cosmos. There are always new discoveries, new puzzles, new wonders to discuss. So as always, I encourage you to do one simple thing: keep looking up. The sky is full of answers, but more importantly, it is full of even better questions. The story of the universe is the greatest story ever told, and it's still being written across the heavens every single night. Let's continue to read it together. Thank you for joining us on this cosmic quest. The journey continues.